Hi everyone, this is Mr. Lee, and in this video, we are going to do the E field for a ring. For this one, it really does help if you have a visual reference. So I have here in my hand a object that resembles a ring. So just imagine a very thin ring. I know it's a little bit thick, but imagine a very thin ring, and it's in a floating space like this. Okay. So as always, let's start off with a quick little sketch. Right. So I want to draw, and the next video after this also relates back to this drawing. So we'll keep it in the same orientation. So this is the ring. Okay, so it's like a 3D image. It looks like this, all right? And so it's kind of slanted so that you can see that it's actually a ring. But if you want to imagine it flat like this is also a fine way to imagine it. And we are at a position here, and we want to know the E field at that point, all right? So a couple of things about this point here. If this is the vertical axis, and this here is the horizontal axis, from uh, the very middle of the ring outwards, radially outwards. We're going to call this uh, length A, like so. All right. So with reference to what's going on, if this is the ring, we're looking at a point right here. All right, so that length is A. The radius of the ring, we are going to label it as X. And the reason for that is because the radial distance from the ring of charge to the point, that's what we're going to call capital R. All right. Now, for these problems, and I'll make a reference to this at the end, we always want to redefine what that radial distance is using the Pythagorean theorem. And so we are going to redefine this as x squared plus a squared. And once again, at the very end of the video, I'll show you exactly why we do this. There's a little test that we do at the end to make sure that our answers make sense. All right, so here's our drawing. And here's a couple of extra pieces of info. Um, so there's a lot of setup to this, and so we didn't even start to answer the problem yet. It's just a setup. So for here, we have a linear line density. Okay, so this is the linear line density of the charge per the length. And you might be thinking to yourself, Mr. Lee, this is a ring. It's not a straight line, but that's okay. Remember in the previous video when we did a arc, that was just a straight line that we bend, and a circle or a ring is just a straight line that we bend all the way around. And so what this gives us is the charge over the circumference of the circle, which is equal to the total charge of the ring over 2 pi, and the radius for this circle, be careful here, is my variable x. All right. And if we, for the sake of the problem, what we want to do is we want to take a tiny bit of charge, and so we call that dq, over a tiny bit of this arc length, right? And here I'm going to do a little side note. So in your notes, do a little side note here. Okay, and that side note is the idea of what is a arc length. So the formula for arc length, and this is on your equation sheet, is arc length is equal to r times theta. And so the cool thing about this is that if you know the whatever the circumference is, you could probably figure out this formula without going to the formula sheet, but just in case it's there. So for a full circle, the arc length is going to be your circumference. And we know that the formula for circumference is going to be 2 pi times the radius. And so if we compare these two formulas, okay, we could actually break it down a little bit more. We know that the circumference is equal to the radius. I'm going to put that in parentheses because I want to isolate it visually, times 2 pi. So what we have going on here is that this theta, okay, that is your full 360. And in terms of radians, we don't use degrees, we use 2 pi as a radian. So that theta is 2 pi, and your r, of course, is just your r. Okay, so this is how you can get the arc length formula if you know the circumference formula. All right. So with that being said, if we're looking at a chunk of a charge or a chunk of this ring, that chunk of the ring is what we just call the arc length, right? And so I'm going to use my formula for arc length, which is r theta. So if we want a chunk, we can rewrite this as, let's see, ds is equal to the radius, which is a constant, times d theta. Okay, and this is where things get a little bit tricky here. This theta here, okay, so let's write this here. So this theta is the theta for the circle, okay, or I guess the ring, because we will have to be looking at another angle, and if you didn't already pick it up, that other angle comes from our triangle. Okay, all right. So here, instead of little arc or little L or DL here, we can replace this with DS, and we know that DQ and DS is just R D theta, like so. All right, cool. So this is the setup. There's one more picture that I want us to include. So this picture here is usually what you'll see on like FRQs or practice problems, but it always helps to be able to draw multiple representations of it. So what I'm going to draw is a flat side view. So this is a side view. Okay, so this is still the ring, and here this is still A, and here this is still R, and this here, the midway point of the circle, well, the radius is still X. All right, so at this point here is going to, this tiny bit of charge, okay, that dq, is going to create a E field, assuming that this is a positive ring. It's going to create an E field that is going out like so. All right, now according to the rules of symmetry, this dq down here will create a E field going like so. And so according to the rules of symmetry, we know that the E field in the Y direction will cancel out. So let's write that little note here. DEY will cancel due to symmetry. All right. All right, so important little note there. So what I want to do here is that this DEY, or excuse me, this little DE, I want to break it down into the components that matter. And for us, the only component that matters here will be our DEXs. So the total E field at that point will just be a summation of all the DEXs as we go around that ring. Okay, so one thing I mentioned is that this theta isn't the only angle, because we also have this angle here of the triangle. So let's label this angle right here. This will be labeled as phi. Okay, and this is the angle for the triangle. Okay. And yeah, we use phi before for flux, but usually for physics and math, after you use theta for an angle, phi is usually the next one that we use. Okay, it's kind of like A, B, C, D. So we go theta, and then we go phi. All right, so if that is phi, this is also phi right here. All right, now this DEX, okay, we're going to make a reference back to it, but DEX is a adjacent side of this DE. And so whenever we do adjacent stuff, we are looking at the cosine ratio, cosine of theta. And so for here, the ratio that I want to focus on are this triangle here that I just highlighted. And so cosine would be A over R. Okay, and R, of course, being the square root of x squared plus a squared, and we're gonna substitute that in at the end. All right, so that is just a setup for the problem, and now let's actually solve it. So in order to solve it, as always, we start off with the E field equation, E Q over R squared, and then we're like, all right, let's get the tiny chunks of E field. Is equal to KQ over, oops, excuse me. we're going to have tiny chunks of the E field created by tiny chunks of the charge divided by this distance r squared. But I want to make sure that it matches what we have up here. And that r squared is capital R squared, like so. And we are looking only in the x-axis. So I'm going to put a little x there. And because we are only looking at the x-axis, we want to make sure that only the x component remains. And so that'll be the cosine of phi. All right, so once again, this is just a setup. And the next step, I'm going to clean it up a little bit. All right, so I'm only going to just change one thing at a time so you can follow along. So we have k here, and this dq that we have up here, we're going to get our dq from this super long equation up here, right? So we know that dq is going to be equal to, so I'm looking at this final part and this initial part is equal to the charge density times rho d theta. Okay, and we want to look at this in terms of theta, because as we're going around the circle, that's the only thing that's changing. Phi doesn't change, our x doesn't change, our a doesn't change, our r doesn't change. It is the angle of the circle that is changing. So we're going from 0 radians all the way to 2 pi radians. So let's replace that in here. To show what I'm substituting in, I'll put it in parentheses. So this will be lambda d theta, is there an x there? Let's see, d theta, oh, and our r, that is the radius, so our radius, I'm not going to write r, I'm going to leave that as x. All right, all over r squared, and our cosine of phi, we define this up here, oh, excuse me, I called that cosine of theta, let's call that cosine of phi. Will be a over r. All right. So a over r. We'll put this in parentheses to show that that was one of the substitutions. Okay. Now we can integrate. So if we integrate the left-hand side, we're just left with e sub x. So that is showing us that only the x component is what matters. And then we get k lambda d theta x all over r squared. Oh, excuse me. Let's actually math this out. So r squared times r, this will be r cubed, and then we have a in the numerator. All right, so it looks pretty funky, but that's okay because a lot of it will come out thanks to the constants. And we're going from 0 to 2 pi, okay, for our radii. All right. Now, at this point, all you have to ask yourself is, what is a constant? Okay, we know that k is a constant. We know that the charge density is a constant. We know that the radius of the ring is a constant, which is x. We know the distance from the middle of the ring to the point that we're looking at, a, is a constant. And we know that the radial distance of the charge to the point, r, is a constant. So all of that comes out. And so it's pretty nice, and it cleans up very well. So we get d theta as the only thing that's left. And so if we integrate that, our final answer would be e sub x is equal to k lambda x a 2 pi all over r cubed. Now this is where we should definitely simplify. Okay, it really helps to know where things are coming from, and so I'm going to do that in the subsequent steps here. So what I want you to see is that here you have 2 pi, and you have the radius of the circle, which is x. Okay, so the things I just highlighted is the circumference. So circumference is 2 pi x. And if you remember, we said the circumference is the quote-unquote line that we just bent. So that's our L, right? And so what we get here, if I were to just rearrange it so that I could put the 2 pi and the x together, we get k lambda a, in parentheses to show that I'm going to take some action with it, 2 pi x all over r cubed. All right, now what I want to do is I want to show you the next thing that I want to combine. We have lambda and we have this 2 pi x. And the reason why I want us to focus on there is because we know that charge density is total charge over the total length, right? And for us here, the total length of this ring is 2 pi x. So if I have lambda and if I have 2 pi x being multiplied together, the highlighted part just becomes q. So we get k q a all over, and this is where I'm going to substitute in our r. So if you remember from above, we said that r was equal to here x squared plus a squared all square rooted, and so that makes our denominator x squared plus a squared 3 divided by 2. All right, and that is actually our final answer. And so at the very beginning of the video, I told us that we want to redefine that radial distance in terms of a triangle for a test. And this is a test. So let's write this down. We define r, aka the radial distance, okay, in terms of the two other sides of a triangle, that should be a right triangle, excuse me, to test this. So in this case, we say if the point away from the ring, which is A, is so big compared to the radius of the ring, what happens? Okay, so using this test, we can say that EX is equal to KQ over A, all divided by let's do it, x squared plus a squared 3/2. So if a is so big that x is so small, that so small number just becomes 0. So what this means is that x squared just becomes 0, leaving us with the formula kq over a squared to the 3/2 power. So for those of you that are pretty math savvy, okay, you can see that it's kqa all over a cubed, okay, and this gets simplified to kq over a squared. Now this a is just a radial distance away from the object. So what this means here is if you take your ring, right, and if we have our radial distance, or excuse me, if we're looking at a point A away, but if our A is so far away, this ring will shrink in size. Okay, the radius basically becomes 0. And if we shrink in size, what we get here is a point charge. So we're looking at a point charge at a point A right here. So we know what the E field for a point charge is, and that is KQ over R squared. And that, my friends, is what we got over here. Just replace that A squared with the radial distance of R. Because when A becomes so big that X gets so small, we can think that the two, or the radius of the ring, it basically collapses, making the hypotenuse and the flat side of the triangle to become 1. Okay, so that is why we redefine our hypotenuse in terms of the other two sides of the triangle. All right, see you next time. What we're going to do is we're going to look at a disk of charge. Bye-bye.